You type a sentence, and a machine paints a picture that never existed. The usual story is that it begins with pure noise, random static with no structure at all. And then it erases that noise a little at a time until a clear picture appears. That is true. But as an explanation, it is almost empty. What is noise here? What does erasing it actually mean? And why does it produce a face instead of more static? Underneath the hype is a piece of mathematics that is genuinely precise and rather beautiful, and there are two different ways of seeing it that turn out to be exactly the same. So let us build it, carefully, from the ground up. Let us start with the real problem. We have a collection of things, photographs for instance, and we want to generate new ones that look like they belong. Here is a stand-in for that data, drawn as points in a plane. We can draw samples from it. There they are. But nobody hands us a formula for the distribution they came from. That gap is the entire difficulty. The idea behind diffusion is to build a bridge. On one end sits the data, which is hard. On the other end, a plain bell curve, a Gaussian, which is trivial to sample from. We connect the two with a long chain of tiny steps, each one nudging the points and adding a little noise until every trace of structure is gone. A single step of that chain is exactly this. Given the previous point, the next one is drawn from a Gaussian. Its center is the old point pulled toward the origin by a hair. And we add a whisper of fresh noise on top, an amount set by a small number we call beta. One step barely changes anything. But there are 1,000 of them, and together they dissolve the data completely. Stack those steps up, and the whole forward process is just one transition after another multiplied together. So to find where a data point lands after, say, 400 steps, it looks like you would have to simulate all 400. You do not. Here is the property that makes everything work. A Gaussian pushed through another Gaussian step stays Gaussian, and when you combine the noise from two steps, the variances simply add. Carry that all the way back to the start, and the noise from every step collapses into a single clean formula. The point at step t is just the original data, scaled down, plus one Gaussian whose size we can compute directly. We write alpha bar t for the running product of all the shrink factors. In one line, x at step t equals the square root of alpha bar t times the clean data plus the square root of 1 minus alpha bar t times pure noise. Pick any step and jump straight there. No simulation required, and this is the schedule. Early on, the signal dominates. As t grows, the signal fades and the noise takes over until almost nothing of the original is left, only a Gaussian. So the forward direction is completely solved in closed form. The entire challenge is the other direction. Can we climb back up the chain, from noise to data? To generate a sample, we run the chain backwards, start from pure noise, and step from xt back to xt minus 1 again and again until we arrive at data. But here is the catch. The exact reverse of even one step depends on the entire data distribution, the very thing we do not have. On its own, it is intractable. Two facts rescue us. First, when every forward step is tiny, its reverse is also, very nearly, a Gaussian. This is a classical result. It holds in the limit of vanishingly small steps. So we are allowed to model each reverse step as a Gaussian and simply learn its mean. Second, and this is the key, reversing from xt alone is hopeless, but if we are also told the original data point, x0, the reverse step becomes exactly Gaussian. Its mean is a precise blend of where we are now, xt, and where we started, x0. And during training, we do know x0. So at last we have a target we can compute exactly. To turn matching that target into one trainable objective across the whole chain, we need a single further idea. To train, we want the real data to be likely under our model. We want to push up the log probability the model assigns to x0. That quantity is intractable on its own. So, exactly as in a variational autoencoder, we maximize a lower bound on it instead. It is called the evidence lower bound. Here is why diffusion is so clean. That bound breaks apart into a sum of simple pieces, one per step. One term just matches the final noise to a standard Gaussian. It has no parameters at all. The last term handles the final reconstruction. And everything in between is a denoising term, comparing at each step the exact posterior we just found against the model's guess. Now, the distance between two Gaussians that share the same spread is simply the squared distance between their centers. So each denoising term just asks the model's mean to land on the exact mean we computed. And when you write both means out, almost everything cancels. What remains is astonishingly simple. The network only has to predict the noise that was added. In practice, we drop the per-step weights entirely, which surprisingly gives even better samples. What remains is the whole training recipe. In one line, take a clean example, pick a random step, add a known amount of noise, and ask the network to guess that noise. That is all. But why should guessing noise let you paint a face? The answer is the most beautiful idea in the whole subject. So what is the score? For a distribution Q, the score is the gradient of its log density. At every point, it is the direction in which the density rises most steeply. Picture it as a field of arrows over the plane. Wherever you stand, the arrow points uphill, toward the regions where data is dense and away from the empty spaces. Knowing this field everywhere is almost the same as knowing where the data lives. Now recall what the network is trained on. The score of any Gaussian has a trivial closed form. It is just minus the offset from the mean, divided by the variance. But that offset, divided by the standard deviation, is exactly the noise we added. So the score and the noise are the same quantity wearing different clothes. Put precisely, the score of the noised data equals minus the predicted noise divided by the square root of 1 minus alpha bar t, a fixed known scaling. That is the whole secret. Training a network to predict noise is training it to learn the score of the data. The same score does something else remarkable. By a classical result called Tweedy's formula, the best possible guess of the clean data, given a noisy sample, is the noisy point nudged along the score. In other words, the optimal denoiser is exactly the average clean image consistent with what we see. One field, the score, and the entire denoising problem is solved in principle. We can estimate that field anywhere we like, which leaves one final question. Given the score, how do we actually turn noise into a sample? The recipe is called Langevin dynamics, and it is beautifully simple. Start anywhere, then repeat one step. Take a small step in the direction the score points toward higher density and add a small kick of random noise. The score keeps you near the data, the noise keeps you exploring. Repeat, and the points you visit are samples from the distribution. Watch what that does. Here is a cloud of points scattered as pure noise, and behind them, the score field we learned. Let every point follow the arrows, with a little randomness at each step. They drift out of the empty regions and gather exactly where the data lives. Noise has become a set of samples. This, in essence, is how a diffusion model generates. In practice, there is one refinement. We start with large noise and shrink it over the run. This matters most in high dimensions, where our estimate of the score is shaky in the empty regions between data. Starting noisy lets the points cross those gaps and find every mode, not just the nearest one. And here is the quiet punchline. The reverse step we derived for the DDPM all the way back from the variational bound is exactly this. A step along the score plus a little noise. Sampling and denoising were never two different things. Let us zoom all the way out. If we take the step size to 0, the whole chain becomes a smooth, stochastic differential equation, a drift plus a continuous push of noise. With the particular choice that matches our schedule, this is what is called the variance-preserving SDE, and it is precisely the continuous limit of the chain we built. There is a classical theorem that runs any such equation backward in time. The reverse equation depends on the data in exactly one way, through the score. And there is even a deterministic version, an ordinary differential equation, with the very same distribution at every instant. Stochastic or deterministic, both need only the score, the thing our network already learned. Which means the discrete recipe and the continuous flow were never rivals. Expand the square root in a single DDPM step, and it becomes, term for term, one Euler step of that very SDE. The denoising diffusion model is the variance-preserving equation, simply written out in discrete time. 2 languages, 1 object. And since we promised the math, not the hype, 2 corrections. First, the word diffusion is a metaphor. There are no physical particles here. There is a precisely defined Gaussian process. The link to thermodynamics is where the idea came from, not what it is. Second, the model is not a lookup table. It learns a score field and generates by following it. That said, with enough duplicated training data, near-exact copies genuinely can appear. It is a real measured failure mode, not the way the method normally works. So here is the whole idea, on one line. Destroy structure with noise in tiny Gaussian steps. Train a network to predict that noise, which is the same as learning the score of the data. Then follow the score back, and noise turns into something new. No magic, no memorized gallery, just a forward process you can write in closed form, and a reverse process you can learn. If you want to go deeper, these are the papers the whole story rests on. Thanks for thinking it through with me, carefully, from the ground up.